the overwinter break.
It has to be summertime.
I'm like a student, or do I have a job?
You're an accountant.
Do they know it's big?
They can, but
You're
So I
going.
just got
You're going back to your parents' house. They don't know anything. They're like, oh my gosh, you're going.
Cool.
He's going back home. So they see you, and you just got like a big giant face tattoo, like a spider or something like that across your face.
Okay, so storm sewers. Things that are missing. So, who hasn't had hydrology? Rainfall, that sort of stuff? The rest of you have? So, in the grander scheme of what you'll learn from Regal and hydrology and hydrogeology, it's just a mouthful. It's so much fun to get it out. And actually, she just called it hydro, right?
Yeah.
Why'd you create the title? She did it. Not like anybody else did. But anyway, now she's listening to this. I'm criticizing her on the recording, so remind me to edit later. But either way, when you get to hydro, you will understand how much rainfall is going to hit a given surface area and what the rate will be and all that fun stuff. There is stuff in the hydrology book because the hydrology book was titled Hydraulics and Hydrology is the textbook we've always taught with for hydraulics. But it made no sense to cover 2 chapters and she's covering a whole book on that topic. So I took it out a few years ago and stopped thinking about it since. But generally, you really want to figure how much rain is going to fall on a given plane and what's going to run downhill and how much water is going to be there and that sort of stuff. So the cool bit is when we get to doing this stuff, we'll have numbers that will be given to you for that rainfall event. And you'll know how many gallons of water will be trying to rush down the stream. Couple things we got to get out of the way. So our fine folks at Jefferson Concrete, who actually is my wife's cousin, so it was easy to get these drawings from them. Mark, can I have some of those? Yeah. You need to start understanding some things about the way we transition pipes into one another and do this. So we usually do it with a catch basin, and a catch basin is someplace where the water drains into and then pipes out of, or we can pipe into it and pipe out of it in the next series of stations. Okay. The top drawing up there with the circle across it is not a really bad rendition of Ghostbusters, but it's the water flow coming in on the right side, trying to go out the left side, but the inverts don't line up. Okay. Water does not like going uphill, even in this situation. So if we were really having that situation happen, we wind up clogging that thing full of sediment, and we wouldn't get water flowing where it's got to go, and then it's going to back up on the street level. Does it happen? Yes. Have I seen it out in the field? No, but I have seen it here in this building. And we literally had a catch basin put in 127B. If you walk in the door, take a left, and you pull up the carpet right there, there's a manhole cover there, and there's a catch basin down there because plumbers could not line up the drain from all this renovation to the rest of the drains in the building. And it was off by like 3 inches. And the best thing about when that happens, you got a lot of high-powered engineers standing around going, how do we make this work? The only way to make it work is put a pump station in. So literally there's a pump station there now to move wastewater from this half of the building out the rest of the sewer. So that's a sewer system, but this is storm sewer. But ideally this shouldn't contain any, well, I want to be careful. That shouldn't contain any hazardous materials, but it's also why we don't pour oil and antifreeze down storm drains. Okay? Because that will mess up things. Yeah.
So if sewage is taken to the treatment plant, where does stormwater ultimately end up at?
Stormwater, if it's been in separated pipe flows,
Right.
will wind up at a catch basin someplace to downside is, if you look at any given moment in a parking lot on a rainy day, how many leaky cars are there that drip oil on the pavement? And the other bit is, think of the asphalt. What's it made of? Come on. Settlers must have gone over this. What's asphalt made of? Aggregates. What else is in that mix?
Bitumen.
Bitumen. What's bitumen made of? Oil products. So as that stuff breaks down in the environment, where's it going to go? Storm sewers. Where's the storm sewer going to go? The nearest large body of water that we could possibly dump it to. And guess what floats on top of water and doesn't settle sediments like into a catch basin? Oil products.
So
Were they
what
winding
you're
up?
saying is we should start drilling the water supplies for oil.
Yeah. Probably in a couple million years you might actually get something. Locally at the moment, I doubt it. But the problem is, and I hate this phrase, but it is the truth to some of it. The solution to pollution is dilution. So it's diluted so much that any of that amount of oil is not regulated. So it's one of those things that the EPA, Department of Environmental Conservation here in New York, say it's okay by a certain percentage. Should be treated. But the problem also, and why Reagan asked this question, I'm hoping Pat was curious, is because what happens to sanitary sewers with all the crap that runs down there, that has to get through a treatment filter center. But the problem is, if you take a rainwater event and take it into a sanitary sewer, it's all going to the treatment plant. And the treatment plant is going to become overwhelmed during a high water rain event. And what is their option? The city of Montreal's option is to dump millions of gallons of untreated wastewater into the St. Lawrence River and send it downstream to the Gulf of Fundy.
Screw those angle funds, am I right?
Well, that's probably what they're getting onto. You know, we don't care about Nova Scotia, Newfoundland. Probably where they're getting their money from. Newfoundland. But they don't care. They don't have a sewage treatment facility to handle it. So because they have a whole bunch of storm sewers tied into sanitary sewers, all lining up the same place. So modern renovations of things, you're going to see projects that will go down the road that are really about separating those two from each other. But even so, there should be some sort of place to allow storm sewers to catch. Which, if we're in, you guys are going to New Orleans, right, this year for the bridge? Oh, northern Louisiana, okay, sorry. Even northern Louisiana, because there's still enough bayous up that direction. But all those sloughs are nature's way of purifying all that garbage out. So if there's oil in there, it'll get caught, picked up, and located. The water will get purified. So ideally, in the whole world on water treatment and water quality, which is why Regal's into teaching all that stuff. And you should design a storm sewer that just goes, I'm going to dump it out the river. Have a nice day.
Yeah, doesn't that seem contradictory?
Well, it is, but remember, there's certain regulations, and everybody follows the regulations to
Except
their
for the
advantage. What's that?
Except for the government.
Well, the government actually, yeah. I said that one time. I took a class on environmental implications of manufacturing, and it was all on life cycle analysis. And so literally they were asking everybody what chemicals and stuff they wash down the drains and that sort of stuff. And I joked around and says the machine shop here actually drains their coolant into the drain, but it's water soluble coolant. It's a vegetable based coolant. And everybody's like, how can you do that? It's like, well, we be the state of New York. You know, and they all died laughing. The truth is, it's only there because it's a vegetable-based product that can go in there and it'd be fine. But it's also picking up metal shavings, it's picking up all kinds of stuff, and we're adding contaminants to it. What happens if a part comes in with some oil on it already from another manufacturing process? water and oil don't mix, it winds up going down. There's a lot of things. And literally, life cycle analysis, you can never do one in your lifetime. There's so many steps along the way that something gets interacted on. Okay? So we always do an abbreviated one, which is not useless, but it doesn't count for every total bit. Okay. So anyways, we are interested in making sure that the invert of the outlet is lower than the invert of the inlet. And the best way to do that is whatever size the pipe is, line the crowns up. And I called it crest the other day, I'm sorry, it's crowns on the top of a pipe. Okay? But a crown, if I line up the crown on the incoming pipe, the crown on the outletting pipe, the outlet pipe, then the bottom of the invert on the outlet will always be lower than the invert on the beginning. If there's two different sizes in the point. If it's the same size, just line them up and they're good. Okay. And if you ever see the DOT out on the highway and they got the big suction vacuum out and they flip the manhole cover off or let the storm drain off and somebody's standing there with suction, they're literally pulling all the sediment out of that catch basin. And they go around and do them on a regular basis. Because guess what we use in the Northeast? A lot of sand, a lot of salt, a lot of stuff that gets places we don't want. Okay. Cool. All right. What else is that? So a couple little more sketches that I put on here last times. Curbs. Okay, so this is actually a curb. Okay, this is my roadway. So we're going to have water that's going to wash down along the curb here. High rainwater event will be something like this. It's all got to go someplace. So I can do a gutter or I can do a catch basin here, which would actually have an outlet down here, and all that water rushes in and everybody's happy. If you see a roadway that actually has standing water after a rainstorm, and cars are driving through and splashing water up, bad design. There should be no water on the road immediately after the rainfall. It should all run where it's got to go.
Is this like I know, like you were saying, how they had to throw like a sewage ejection pump in because they didn't have the gravity to get to where they needed to. Did they ever run into that with this, or would they just try to direct it somewhere else?
They would try to redirect it, or you dig deeper. So you think about digging this, you're going to lower your pipes down so there's a pitch to it. Right. So everything runs downhill, but then we increase the size of the pipe if we have to, get more flow in there. So it'll come out when we do some of the problems here.
But they want to put a pump in these systems?
No. Actually, so sanitary sewers. There are places where the water treatment facility is higher in elevation than the lowest part of the city. A good one I recognize is Hewelton, New York, has this really stupid little area down by the Oswegatchie River that actually is 45 feet lower than the water treatment facility on the other side of town. Okay? So they literally have a pump station in various locations to pump all that up. Now, these aren't just your average pumps. These are pumps that can handle sludge. Okay? So they hopefully grind it up a bit and they can pump it as a liquid with some solids to it. And eventually go to the sewage treatment facility. And then it gets treated, and then it goes out to the Oswegatchie. Okay? Great place to fish, by the way. Or the discharge of the sewage treatment facility. Fish love all the nutrients. Okay, so ideally we want to plan for that stuff to go on. A couple of the other sheets that we got here from Jefferson Concrete is manholes. So notice the difference. Catch basins they can be rectangular boxes or they can be circular cylinders, but this one's particularly is a rectangle. And if I'm not mistaken, I think this is the standard box that the city of Watertown uses. But then they have manholes. So what's a manhole? Access point to get a person down in there. Okay. So first rule of manholes is this: never go in a manhole. You will. Somebody will have to. But the first thing that has to happen is it's called a confined space. Okay, so there's regulations about how to enter a confined space. You have to test those confined spaces to ensure that there's no gases in there that are going to suffocate you. And that means you don't stick your head down in there first to see what happens, or you will wind up collapsing in the hole, and then somebody else can have to get your body back out of it. After they figure out what caused you to collapse in there first without any oxygen. So anything that looks like a confined space, do not enter. So if that cupboard right there was big enough for you to walk into, you would never walk into it and close the door, because you don't know what gases are in there. Okay? The confined space can be literally, well, the what's the steam thing called?
Distiller?
No, not the distiller, but the sanitizing. Yeah, where you stick the petri dishes in and she. No, not the cover. Steamer. No. Ronnie, do me a favor. You see the goofy thing with the blue labels on the top? Go read the name off that. I'm not going to get it right now.
Yeah, pick the guy with glasses.
Hey. What's the matter with people with glasses?
Oh, there's no people with glasses.
What is it? Steromatic, yeah, that's the name. Product name. Anyway, that goofy little piece of equipment, the name will come to me after I get done this explanation. You look into that, that is actually a confined space. Now, would you stick your head in there? There's no reason to. But you could. Okay? Your oven, if you have a natural gas stove, is a confined space. Should you stick your head in there? No. If the gas is leaking, you're going to be dead. If it's cooking, you're probably going to be dead. One way or the other. Don't stick your head in there, okay? So the same thing with manholes. You don't go into confined spaces without first checking to make sure there's no hazardous gases in it. Because there are gases that are heavier than air that will settle on that spot. And if you get down in there, you're going to hate yourself. Okay? The other thing is when you go into a confined space, you go in the harness on, and you'll see these, when they're working on them, they will set a tripod up over top of it with a pulley system, and the person going down in there is in a full body harness. And yeah, okay, there happens to be rungs on this thing, but the reason they lower them down on a harness with a cable is if they do collapse, they can pull them out without putting somebody else at risk. Okay, so as corny as it sounds, the safety harness isn't for your safety; it's for everybody else's safety. Okay? Hopefully, you get you out before you're dead. But now the other thing is the tops of these, depending on the diameter, is usually fairly large. We'll have pipes come in and out of them. We got other reasons for them. But how do we get it so it fits the average circular manhole cover? We put a cap on top and taper it down in. So when you order a manhole, you usually order 2-part pieces, okay, to match whatever you're trying to job to do.
I did that recently, and they were doing that this summer near Waddington. Is this place between Messina and Waddington?
Yeah.
Yeah.
So, anyways, you need this. The tops are usually round. You know why they're round? Anybody ever driven across a manhole cover?
Yes.
They go punk. Really crappy design. Somebody forgot to bring the thing up level. Or there's dirt underneath one side of it. Why are they round?
So they can't call in.
So
So the
covers can't fall in. You can't put a round cover through a round hole. Swear to God. You think round would fit through a round hole? No. You'd have to have the manhole larger than the cover, but then the cover would fall through and it would never sit there. But the cover, as it sits on the manhole, has a lip around it, and it will not fit through there. Can you get a square cover through a square hole?
Get really
Yes.
unlucky.
Turn it 45 degrees and it'll drop through like, a nice too hot butter, and bang, it's at the bottom, and then you got to get it up. So that's why they're all round. Other than it's a tradition and
Was that always how it was, or did something happened and they're like, all right, yeah, let's change it to?
I think someone got smart enough one time, Jake, to actually know that round doesn't fit through a round opening. Doesn't mean they hadn't tried other things.
John Round manhole cover. James Square manhole cover.
Yeah, go ahead, Owen.
So about the whole regulation with matting harnesses going into manholes, is that regional? Because I would assume, like in the local area, like here, the sewer systems aren't really big enough to where that's a big concern. Where whenever you do anything in a manhole, you have to have a whole crew of dudes and they get a harness on a guy to lower him down. I can imagine that in like New York City or a bigger city.
Oh no,
that's everywhere.
it's everywhere. It's
for
a
everyone,
regulation that you cannot supersede.
including private companies.
Yeah. OSHA has governance over companies of certain sizes. Raiden, his own little company, it's only him.
Took a manhole for 3 days ago.
Yeah. Didn't follow any of it because it's only him. But if you get OSHA takes governance on companies
Also, the
with
safety
45 or more
don't
employees.
apply to privately owned
Outside the law.
You're
So-
outside the law.
There's a regulation for OSHA to come down and inspect. I think it's 45 people. Then you cross into the realm of OSHA can come in and look at you. Then you better be compliant. But if you look, telephone company, when they do any work underground, truck pulls up, they put a little barrier around it, they put up their little rig, and somebody gets in the harness and down they go. Okay. The fiber optic cables guys, they do that because someone goes underground to bring up all the extra fiber optic, to bring it up to put it in the truck to do the splicing and stuff. So all that's there is part of that protection for people. So yes, if you're a mom and pop shop, they don't care if you commit suicide. And it's one of those things that's probably better for the Darwin Award than anything else. You guys know what the Darwin Award is?
Yeah.
The idiots who do stupid stuff get awarded after they're dead.
So what you're saying is hire 44 people.
Yeah, if you can. there is a point where the government will step in.
Those companies
And it's not.
they would have to buy all that.
Oh yeah, this isn't something I'd expect the employees to own.
Yeah.
And then they got safety inspections on it and all kinds of this. So you go back to construction management, that's all your overhead costs. Anyways, so OSHA takes governance, but Department of Labor also has say in it. So, because they're trying to protect the workers' rights. So there's a, I guess the word's a myriad of regulations that all converge at the same point, but all have different purposes. And thou shalt not violate any one of them, or you're SOL. Okay, manholes, covers. The covers, I talked about them being round. There is this piece of steel that goes around the outside that anchors down, and there are pins here, but they're actually, when they put this piece on top of the manhole cap, there's usually some bricks laid in here to give it the elevation adjustment. And if they repave the road enough times, you'll see them when they're repaving the road, they will pull those out and get in and remortar some bricks on top of the old bricks, okay, and then set them back in. So it's not like there's screws that are anchored down in there, it's just holes they put pins in and call it done. But they're wedged in between some, well, what's called pavers, little 1 inch and 2 inch bricks out of concrete that they lay in and mortar them down. Okay. All right. Another cool fact. They're always made of cast iron. Just have always been and always will be.
What are you doing that flange breaks?
You get a new flange.
Oh, that's replaceable.
Oh yeah. This whole thing is, so literally everything from here up is replaceable, and this is where we're putting that flange. and then putting a cap on top of it. And you got to adjust this final height between here to match the roadway surface. Okay. So ideally, you want to order the right basin of the manhole to put the cap on to be at the rough number where you can use a 2-inch paver and be done. Okay. Because it's not fun cutting those things into smaller slivers. And you can't have it. Well, you can actually see it. There's a couple manholes down on Main Street down here that everybody swerves to the right to avoid because the tire goes thunk, 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 thunk. It's like, yeah, they paved it, but they didn't raise the manhole.
Why do they have like a manhole like on the road? They're like staggered all the time. That's not strategic? That's because they just have to miss like something that was underground. They needed a.
So it's a combination of things. So part of what we're going to do between now and then next Friday is we're going to lay out some storm sewer designs.
Yeah.
Ideally, if in a perfect world you could put them to all be in a row.
Yeah.
But yeah, there are other things that get in the way. So there happens to be fire hydrants, and we got all piping for water pressure for fire hydrants, and then you got electric utilities that are buried underground, and you got if it's New York City, you got steam lines, you got gas lines, you got electrical cables. You got stuff left over from the subways that got buried and abandoned there.
Yeah.
Literally, when they dig up a hole in New York City, they have no idea what they're getting into. They think they know, but they literally could be cutting a 1906 subway line track if they did it right. Just stupid stuff left behind. Okay. By the way, when you do buildings and you're working and designing buildings, don't leave things abandoned in place. It's worth budgeting to take stuff out of the building that's no longer going to be used. It's cheaper to leave it there, but literally if you leave it there, eventually someday someone's going to find it and you're going to have to deal with it. So it might be you again in the next job for the same company. Okay, cool on culverts and not culverts, but storm sewers and catch basins and parts and pieces that go with us. Okay, cool. All right, let's go see if my page updated. Why didn't you update? What the hell's going on here? Okay, cool. Well, what I wanted was the page I gave you guys. I don't know where it went. Let me go get it. Okay, copy. Actually, tell you what, we're just going to cheat. I'm going to move the whole thing over and be faster. To here, lectures. Copy. Okay. Speed versus me drawing a lot of crap. Okay, so let's talk about City of Atlanta has a site using a design chart like table 12-4, which we'll show you down here in a bit. Complete the hydraulic design. Key parameters are as follows. Storms, design storm 25-year pipe material, reinforced concrete manning 0.12, minimum pipe size is 12 inches. Okay. You're going to get to do a lot of guesswork here and have some fun coming up with things. And we're going to take a look at what can flow, what can't flow. Okay. The other bit is just for those who haven't had the fun of doing hydrology. Q is equal to the flow rate times the acreage that the rainfall is hitting. The rainfall intensity, we usually measure in inches per hour. If you get 6 inches per hour, you're getting a flood. If you're getting half an inch an hour, you got enough water to deal with. Most things are, you'll get 3 inches of rain in a 24-hour period. It's different than having 6 inches per hour. Okay? And then C is the coefficient of the surface. Everything's got a roughness factor to deal with. So that coefficient of the surface is it a grassy knoll? Is it a tree infested, not tree infested, that's the wrong word, tree laden piece of land that you got to deal with. Okay, tree infested, yeah. There's a whole bunch of environmental people out there just screaming at me right now. Okay, so they're going to give you segments to deal with. Okay, so let's see if I can get some of this in here without losing too much of it. You take your roadway, in this case, we're going to put the storm sewer in here, and you divide your land into segments. So segment 1 to 2, or if you want to think of this as stations, okay, but 1 to 2, we got 1.24 acres of land that we're going to deal with. Our roughness is 0.46. It takes 18 minutes for the water from the top end to wash down to my road, okay, and we have a slope of 1.8%. Therefore, we can go get our Qs, okay. And then segment 2 to 3, we got the following conditions there, a little less inclined, and then 3 to 4. So ideally, you are coming up with your stations here. So 1 to 2 was here, 2 to 3 was here, 3 to 4 is there, okay? And we're accounting for all that water, all right? So the water here is rushing this way. That's not a good place to put that, was it? Rushing like that down to here. And then we're dealing with water that's coming down possibly from another road this way, okay? And then we're going to feed it all out to a stream out here front station 4, okay? But we also get water coming this way across that whole section. If there is a surface that could possibly have rain runoff, you're going to map it out. For you guys, just to give you some heads up of where you're going with this, there are ways to do this with contour maps, and the rest of you know about going find a place where it's 90 degrees and draw a line, go to the next contour, draw a line, and eventually you're going to find out where the channel would be for all that water running down. That'd be the ideal spot at the bottom where we put the catch basin. Okay. Then we know we're going to drain it off. Now, the cool part of this is anything above 1, do you think there's water that's falling there? Above station 1. Is there going to be water there? Probably. Unless you just have one of those localized rain showers that you can drive in and out of in 10 feet. Okay. Those are weird. They do happen. They're usually about 10 feet, but they're usually like quarter-mile distances. But if you drive through and it's like it's not raining there, but it's raining here. That happens on roadways. But generally, you try to account for as much rainwater as you possibly can. Okay. All right. So in doing this, we need to calculate all our Qs. It's going to go down each one of these pieces. Okay. So we have a Q of 1 to 2. We're going to have a Q 2 to 3. And then we're going to have a Q 4 or 3 to 4. Okay. And we have to account for that. But what happens at station 2? It takes a little turn, yeah, it does that. But what happens at station 2? Is it just the Q from station 2 to 3 that I gotta worry about?
No, because
It's cumulative. No, you're getting close, Leo. But not quite. It's cumulative. So from station 1 to 2, let's say I get a flow rate of 20 cubic feet per second. Okay, and at 2 to 3, I get another 35. What's my total flow in that pipe from 2 to 3? Q1 to 2 plus Q3 2 to 3.
Yeah, that's what I was getting at.
Yeah.
I didn't finish that.
Make sense? Because if you don't add it up, guess what's going to be wrong? Water's going to be backing up in the wrong places. So if you increase your flow size or your flow rate, what you do with your pipes, you're going to make them bigger. Okay. Now maybe not always, because remember, in certain pipes we can have a certain amount of flows that we can deal with, and whether the pipe is under neutral, under the center line, or if it's above the center line. As long as we don't cross the 94% full line, we're good. Water will still go down through there. Just how fast and how far it will go. So all those things you've done in the past so far for me is part of that. Okay. All right. Mannings, same equation, doesn't change, but we are interested in the velocity of what can be discharged down through there in the openings of the pipe. Okay. And we still got the hydraulic radiuses to do. Okay. All right. So steps to this thing. Best way to define this is, one, determine the grading. By that I mean slope. Look at slope. Look at rainfall, intensity, intense. Okay, get all that down. And then spacing, we're looking for an inlet that has a velocity of 4 feet per second. Okay. So we really want to keep ourselves under that, because 4 feet per second is still quite a bit of velocity. Think about that. I got to go 4 feet, so I got to go from here to there in a second. Okay, and I got to get all that water moving down there. So we give you a ballpark to start with. What's your first pipe size? Max distance between catch basins should be no more than 250 feet. 3, you got to take a look at changing directions, because that's like putting a 90-degree elbow in a domestic water line and trying to get the water from the tower down to the building and have the most pressure you can keep. And when I put a catch basin in and I turn things 90 degrees, it's going to turn. By the way, these are not piping systems that come with fittings. The fitting is the catch basin, okay, or a manhole, depending on what you're trying to do. All right, and then we got to look at the slope and the pipe size. Cool. All right, you'll wind up getting a chart that looks like this. Okay. All right, so inches per water, so 5.6. I think that was given to you up here. Where'd 5.6 come from? Well, when we come back to doing these on Monday and actually do this, I'll explain where that 5.6 comes from. It's not in the chart, and it's not in the table. We got 1.4 acres. We got 18 minutes of time to go from the top to the bottom. And for right now, we're going to fill a chart like this out. Peak runoff. So we're going to calculate our cubic feet per second based on the ACI equation. And then length of pipe, we're making choices. Okay. So from the first 1 to 2, we put 140 feet in. And by the way, that goes center to center. Center of the catch basin to center of the catch basin. Okay? So not 140 feet of pipe directly, but center of the catch basin, center of the catch basin. Okay? And we're going to go pipe slope. And we try to match the slope of the land. Okay. Nice thing is Mother Nature designed a lot of land to run downhill. Why not use it to your advantage? Why create piping systems that dig deeper than that? Okay. Then we choose some pipe sizes, and we choose pipe capacity again based on that. Okay. So we got our Q of the runoff, and we're looking for our Q that we can discharge down that pipe. And then we're going to check our velocities to see how we're doing. Okay. And then we're going to take the length of time that travels to get from station to station. Okay? Cool so far? Cool. One last thing. I know you're trying to write this down. Don't worry about it. I'll bring it back up and give it to you. You remember someplace along the line here, I showed you this goofy little thing. Maybe did I? Okay. I'll get you a copy of this. But this is what you can discharge through different size pipes, and based on the hydraulic element, okay, and we can determine the depth of flow through this. Okay? And it's in percentage. So if you get 80% of flow through here, we come up and we have it 66% deep inside that pipe. Then we can come over and actually see what our velocity is going to be and what our hydraulic radius would be out here. And when the two velocity and hydraulic radius mesh right there, what's happening? The hydraulic radius, that portion of the water that's in there, matches the velocity on that curve. We can't do any better. Okay. Now you get to the next pipe. Okay. So I'll show you how to play with this down the road too. But today is a good introduction of all this stuff that goes on with this. Okay. And remember these guys? They're back. Actually funny, Jake asked me for some help and I went, oh yeah, where's the textbook? I grabbed the textbook and flipped over to a 60-inch pipe and went, oh yeah, you look here and this is the normal depth. It's like, oh shit, that wasn't what we were trying to do. This was the equation you had to use. Trust me, if you can use this, you don't use the equation. Okay? So we're going to come back to all that stuff and I'll explain some more about this. And somebody asked me the other day when we were doing the culvert design about the velocity. So up this side of that chart is your velocity based on the roughness of the pipe. So if I come up, in this particular case, we'll go up here, come up, and I hit my velocity, or hit my slope, and I come across, I can figure out what the velocity is inside that pipe. Okay? So between this chart and the other one up here, make your life a lot easier doing these storm sewers. Or, yeah, storm sewers. Okay? Almost want to say sanitary sewers. Sanitary sewers, all bets are off. A whole new set of rules to deal with all the sludge that goes down with that. Okay. Cool. Everybody good so far? Okay, that was a crash course on what you're going to do for the next week. Save those, that sheet. We'll fill in some more details on Monday.